The universe is a big place. Billions of interactions and reactions happening in the blink of an eye. But something binds these happenings together. Not a force, but a natural tendency, holding true from gargantuan nebulae to imperceptible particles. This natural law, the movement towards disorder, is known as entropy. The origin of our understanding of entropy starts with the publishing of
Réflexion sur la puissance motrice du feu et sur les machines propres à développer cette puissance.
or Reflections on the motive power of fire and on machines fitted to develop that power, for those of us who don't speak French. This writing was produced in 1824 by Nicolas Leonard Sadi Carnot, a French mechanical engineer. You see, the heat engines, a mechanism designed to convert heat to work, of his time were horrendously inefficient. Energy was lost in the conversion from heat to work through transfer into the material of the engine. Inspired, he abstracted the Carnot cycle, a theoretical system that converts incoming heat to work with maximum efficiency. Though he did not know at the time the amount of pain and frustration this concept would cause to undergrad students centuries later, his system would define the study of heat transfer to present day. The German scientist Rudolf Clausius would later build on Carnot's original heat engine principle with his statement that heat transfer cannot occur without the occurrence of work. William Thomson, perhaps better recognized by his title Lord Kelvin, would concur with Clausius, stating, "It is impossible to derive mechanical effect from any portion of matter by cooling it below the temperature of the coldest of the surrounding objects." In other words, that the existence of a closed system that converts heat to work without effect of its surroundings is an impossibility. These three statements, combined with others, would form the basis for the second law of thermodynamics, the law of entropy. The second law of thermodynamics states that for an irreversible physical process, the net disorder, or entropy, of a system and its environment will increase towards a maximum value. In other words, the final state of any closed system is disorder. This can be illustrated with the common example of a bedroom. If you're anything like me, over a week of routine usage, it will become quite cluttered. Yes, you can organize the room, but this results in an expenditure of energy. Given another block of time, the room will return to its natural state of disorder. Over an amount of time approaching infinity, energy to organize the bedroom will eventually run out and become inaccessible, and the bedroom will be left in a messy state. But Andrew, my name is Andrew by the way, how does this relate to chemistry? For the relationship between entropy and chemistry, we turn to Ludwig Boltzmann, who famously stated, "But what if we went smaller?" To understand Boltzmann's relation, you should first understand the difference between macrostates and microstates. Look at this balloon. Its pressure, temperature, and volume are fixed. It is at equilibrium. If we look at the inside of the balloon at the level of atoms, we see that the balloon is home to a state of disorder. Particles are at random position and velocity. Though they could theoretically arrange themselves in some organized alignment, it is much more likely that they will be observed in some chaotic arrangement. Knowing the particulars of a certain microstate can tell us about the macro, though the same cannot be said about macro to micro. Boltzmann asserted that for any macrostate in equilibrium, there are a certain number of microstates that may comprise it. One way to think of this may be to envision a Rubik's Cube. Let's say we want 3 red squares facing a side. There are many different combinations to achieve this goal. We can see from this that for the macrostate, 3 reds, we have many different possible microstates. Boltzmann found that the disorder of a macrostate can be measured in energy given the number of microstates possible, producing this equation to describe it. This relationship is important as it makes entropy quantifiable. What does that mean? We can compare different substances and states based on their measure of entropy. As chemistry students, we can use this to draw preliminary conclusions or help us with problems where all the information is not immediately available. For instance, A difference in entropy of two closed systems of equal volume and temperature can let us know that one contains more particles than the other, or that the physical state of the particles is different. And if you ask me, that's pretty neat. Looked at from a universal perspective, entropy can be a bit of a bummer, as the second law of thermodynamics describes that it must always increase in a closed system. In a way, it's intelligent life's death sentence. We all move constantly towards annihilation in a final environment that will not support an organized form of energy to result in sentient life. But in an odd sort of way, I find this comforting. It provides all the more reason to live your life the way you want to for your short stint here, to enjoy the short but fleeting ride as a microstate of the universe. Because you only get one shot. Entropy makes sure of that.